Okay, so welcome back to another video. Here's a little nice inverse trigonometry problem, and it's dealing with inverse cosines, and we have to find solutions x such that inverse cosine of x plus inverse cosine of 2x is equal to 3 pi over 4. Actually, I didn't even write the domain because it's actually, for one, if you think about a cosine function, it's actually a bounded function. If we're doing this with the opposite, it actually falls in between specifically -1 and +1. But here, if we're dealing this because we have x and 2x and take that sum of that actually differs between that domain. So if you look at this, it's actually bounded from the solutions we know for x has to exist somewhere between inclusive -1/2 and +1/2. And so with this little notion, we have to be a little bit careful on how we choose our solutions. But and I say that way so at least we know that we have to solve this entire thing to get the solution using standard trigonometric identities and formulas. But again, with that whole domain, you want to make sure that it falls within that range. Otherwise, anything outside of that domain is always going to be specified as undefined. So with this, just a lot of trig identities we're going to be using, and as you can see that eventually there will be two solutions, but however, there's actually one of the solutions that's going to exist that works because one of them will not satisfy this given solution. So we're about to find out what that solution is going to equal to exactly that satisfies the following. So with that, let's actually just get started. Suppose if we start off this with our given equation, I subtract the inverse cosine of 2x to both sides, so we're left with inverse cosine of x equals 3 pi over 4, subtract inverse cosine of 2x. Now, if I just take the cosine of both sides, so cosine of inverse cosine, so that's just left with x by itself, then cosine of 3 pi over 4 minus inverse cosine of 2x. So for one, this is just going to be left as x. And then on the right-hand side, we can actually use the identity for the difference of inputs for cosine. So that actually leaves us with the following. So the difference says that if you have a and b of the subtraction, cosine of that input is going to be cosine of, specifically first we have 3 pi over 4 multiplied by cosine of inverse cosine of 2x. Okay, and then we add this now, they're both sine functions, so this will be sine of 3 pi over 4 multiplied by sine of inverse cosine of 2x. All right, so here's some values that we know that we can actually do just a little bit of substitution. I'm going to start off with the big one here, and that's specifically if we look at the sine of inverse cosine of 2x. That says that sine of inverse cosine of 2x, that's actually simply just going to equal to the square root of 1 minus 4x squared. And so that proof follows by the same thing with a similar trick where if you set one of the values as, sine, then what it does is that you actually use, the whole Pythagorean theorem triangle to find that missing side, and then eventually you actually get into this, the length, you get the length as the value. And so with this, we just plug in that input to get this value. It's a very, very simple proof. There's a bunch of resources to follow with that method, basically. So I just skipped the steps for that. So we know that another value is cosine of inverse cosine of 2x. It's basically just like what we did, the same thing over here. So that cancels out. So that's going to be just 2x. Another value that we are going to use is we know that cosine of 3 pi over 4 is going to equal negative the square root of 2 divided by 2. I'm going to leave this as -1 divided by the square root of 2. Same thing over here. Sine of 3 pi over 4. This is actually just going to equal to positive square root of 2 divided by 2. I'll just leave this as 1 divided by the square root of 2 over here. And so with that, now we can actually make some little substitutions for all these values that we actually just computed. Well, for the most part, not exactly explicitly, but anyway, so we just plug all this back in. So we have x is equal to, first we have negative square root of 2. That's just coming from cosine of 3 pi over 2 multiplied by 2x. And add this with, so plug this back, so there's going to be 1 divided by square root of 2, then multiplied by the square root of 1 minus 4x squared. And so from here now we can actually simplify we can actually now perform the multiplication. So far we're going to have, this is going to be negative 2x squared divided by square root of 2. Add this with the square root of 1 minus 4x squared divided by the square root of 2. And so from this now, what I can do here is they share a square root of 2. I'll just multiply the square root of 2 to both sides. So that means we have the square root of 2 multiplied by x, and this is going to equal minus 2x. So everything from the square root of 2 from the denominators both here are just going to disappear. So plus the square root of 1 minus 4x squared. We can actually just add the 2x to both sides. So at least this makes it helpful. So we were trying to separate all the constants and variable on its own. So plus 2x equals the square root of 1 minus 4x squared. Now I can just factor out the x. So we have x multiplied by the square root of 2, add this with 2, equals the square root of 1 minus 4x squared, x and then we'll plus over here. And now we can simply, it's a lot of algebra. I think you can see like where we're going from the beginning and then all the way to the end. It's actually a little straightforward, nothing too, difficult or out of control. So from this, I'll square both sides. So we're gonna have x squared, then multiply by the square root of 2 plus 2 quantity squared, and this is equal to 1 minus 4x squared. And so let me just expand this expression out. So this is x squared, then if you just perform the FOIL, so this is gonna be 2, add this with 4 times the square root of 2, and then add this with 4, and equals 1 minus 4x squared. What I can do here is they both share x squared, so I'll just add up x squared to both sides, x squared, then followed by this same expression over in the parentheses, and add this with 4x squared, and set this equal to 1. Now I can actually just factor out that x squared. So now the 4 will go inside this parentheses, so x squared times 2 plus 4 times square root of 2 plus 4, and then plus 4. And that's just going to equal 1. If we just add this entire thing in that parentheses, this is just going to give us 4 times the square root of 2. 2 plus 4, 6 plus 4, 10, and then equal to 1. Then I can actually just divide both sides since it's just a constant. So x squared is equal to 1 divided by 4 times the square root of 2 plus 10. Take the square root of both sides, and so we end up with that we have 2 values. X is going to equal plus or minus the square root of 1 divided by 4 times square root of 2 plus 10. So I know, as I said before, we have 2 solutions, but one of them works. You can easily see that if you were to check and see that if you plug the negative back into our given, then you'll notice that it's actually going to give a different value, that it does not satisfy the 3 pi over 4. However, if you do plug in the positive radical, so positive square root of 1 divided by 4 times square root of 2 plus 10, then indeed it actually does satisfy that equation. So we can disregard the negative radical, and so our only solution is that x is going to equal positive. And it makes sense to see that because if you were to graph the given equation, for one, there are no 2 x values that actually equal the same y value. If you think of it, this is more like this is treated as a odd function. So from here, then we could say that x is equal to just the positive square root of 1 divided by 4 times the square root of 2. Add this with 10. And so just like that, we have found our solution to the given inverse cosine equation. And this is actually, that's it. So just like that. With tricks like this, it's a lot of trig identities in algebra. It actually takes you a long way to get over here, and then it makes it satisfying. So yeah, that's pretty cool if you ask me.